Hello, welcome to another module in this massive open online course. So in this module we'll start looking at a different topic, which is channel coding. Alright, so far we have seen source coding, and now which is basically we said to represent the symbols of a source efficiently in terms of bits. Now we'll start looking at a different aspect of communication, that is communication over a digital communication channel, which is channel coding. Okay, so we want to start looking at a new topic, which is channel coding. Okay. Now, as we have seen in a communication system, what we have is we have a binary message, which will pass through some block. I am going to name this block later, and that passes through the channel, followed by some other block. We are going to name these blocks later, and followed by the output. Okay. So naturally here at this point we have to have we have to be able to estimate. Alright, so this is the recovered message. Okay, so let us say we are transmitting the binary message 0, 1, 1, let us say any arbitrary message. Okay, so we have this is the transmitted message. Okay, and the corresponding received message or the reconstructed or the corresponding, let us say, received message. Okay, not the reconstructed. We are talking about, let us say, at this point. Okay, let us make this fine distinction. Let us make this as the received message. And let us say the received message or the equivalent received string, and remember we are looking at digital messages, therefore we are looking at a sequence of digital information bits, binary information bits, that constitutes a digital message. Okay. The received message can be something like 0, 1, 1, 1, 0, 1. And if you observe this thing, what you will see is while the transmitted message is 0, 1, 1, 0, 0, 1 followed by the rest of the message, the received message is 0, 1, 1, 1, 0, 1. So if you can look at this position, there is an error, okay, in the received message. The transmitted bit is a 0, received message or received bit is 1. So there is an error, or more specifically there is a bit error. Okay. So this bit error arises over the channel. So there is a bit error over channel, or arising due to basically the noise in the channel. This arises basically due to the noise over the This arises due to noise over the channel. Okay. So, we need to be able to correct such errors which are arising over the channel, right, because we are transmitting a stream of digital communication bits, of digital bits which constitute the digital message that is transmitted over the channel at the receiver, correct, due to noise over the channel, correct, due to the noise effects of the channel, the received message or the received sequence of bits, the received digital message is not in accordance with or is not identical to the message that has some bits are in error, alright, which arise due to the these bit errors arise due to channel imperfections. At the receiver, we have to be able to recover from these garbled bits, that is, recover the errors which are arising, recover from these bit errors or errors in the message which are arising due to the channel imperfections. Okay. So, at receiver, so we need to be able to correct the errors to the best we need to be able to correct the errors to the best possible extent. Now, remember, we are not looking at correcting, all the errors. It might not be it might not be possible, right. In fact, that is what Shannon's capacity theorem tells us, that is, it is only possible to communicate with a diminishingly lower, that is, with a diminishingly lower probability of error. So, it might not be able to recover from all the errors, bit errors that occur over the channel, but we will try to attempt, right. It is our aim to recover, that is, correct this digital message to the extent, to the maximum extent that is possible, that is, to recover from as many bit errors as possible. That is the idea. We might not be able to make the bit error rate exactly 0, but the idea is to make it as small as to make this probability of error as small as possible. That is the idea. Okay. So, we need to be able to correct the errors to the best possible extent, that is, need to make bit error rate as low as possible. Need to make the bit error rate as low as possible. Now, the question now arises, how does one do this? How does one do this? Let us look at a simple example. To eliminate bit error, let us look at a very simple example. To understand this better, I am going to look at a very simple example which might almost be something that is rather inefficient, as you are going to see shortly, correct, but for the sake of understanding, let us go back again to our transmitted sequence of bits 0 1 1 0 0 1. What I am not going to, so this is the transmitted sequence, that is, sequence of bits to be transmitted, not transmitted, this is now to be transmitted. Okay, what I am going to do now is I am going to repeat each bit. Instead of transmitting 0, I am going to repetitively transmit each bit 3 times. So, 0, so now this becomes my actual transmitted, or let us put it this way. This is the transmitted series of bits. Okay. Now, let us say if there are some bit flips, for instance, let us say the first bits are 0 0 0, this bit 1 1 1, the first bit 1 flips to 0, rest are intact 0 1 1, the next also, let us say this bit flips 0 1 1, let us say next are received correctly, 0 0 0, let's say this bit flips, the last one flips to a 0 and so on, of course. So what we have seen is this bit is flipped, this bit is flipped, this bit is, so I am using the arrows, flip or basically bit flips arising due to errors, correct. These are basically, you will realize, bit flip or error, basically a flip or a bit error, okay. So what we have is, we have bit errors, but while decoding you can see that there would be no problem, there wouldn't be any problem, because if you use a majority rule or majority logic decoding, by majority logic decoding you mean that we are repeating each bit 3 times. So if 2 or more of the bits are 1, then you decide a 1, or if 2 or more are 0, then you decide a 0. This is known as a majority logic. It's a very simple rule, that is, you look at each bit group of 3 bits, assign the majority, assign the decoded bit to the bits which are in a majority. If the zeros are in a majority, then assign a 0, if the ones are in a majority, then assign 1. For instance, here we have 3 zeros, so this will obviously be a 0, correct. So this will be 0, 0 1 1, 2 bits are 1, so this will be 1, 0 1 1, again this will be 1, 0 0 0, again this will be 0, majority is 0, 0 0 0, no question, this is 0, 1 1 0, majority is 1, so this is a 1. So basically we have got our, this is our decoded, so this is our, let us not use the word decoded, this is our reconstructed. So now you can say this reconstructed, despite the errors, the reconstructed bit sequence is identical to the transmitted bit sequence, okay. So now you can say we have recovered, in principle, of course there are a lot of problems with what I have talked about, in principle equals the transmitted bit sequence, reconstructed bit sequence is equal to the transmitted bit sequence despite the bit errors, which implies that we have been able to recover from the bit errors, okay. Which implies that we are able to recover from the bit errors, okay. We are using a majority decision rule. Now here we are using a majority decision rule, that is also something that you should remember. Majority decision rule, okay, and that is very obvious what you are. Now observe, therefore, now the first observation that you can make is, observe that to be able to detect or correct errors, this is important, to be able to correct errors we need some form of redundancy. For instance, here we are repeating each bit 3 times, although we do not need to do it, we can transmit each bit a single time, but here to be able to recover from the errors we are repeating each bit 3 times. So we are introducing redundancy in the system, okay. So to be able, so that is the first point, to be able to detect, to be able to detect or correct errors, we need we need redundancy. Okay. For instance, example, we are taking the bit 1, we are repeating it 3 times. Repeated 3 times. Now, this process, right, this process of systematically introducing redundancy to be able to detect or correct errors introduced over the channel, right, introducing systematic redundancy in the transmitted bit stream to be able to detect or correct errors is known as channel coding. And the particular code, that is the particular format of redundancy that is employed, that is known as the channel code or an error control code. Okay. So the point is, okay, this process of introducing systematic redundancy to enable detection or correction, for that matter, and detection and correction of errors over channel or introduced by the channel is termed as channel coding. So this is basically termed as channel coding. Okay, so this process of systematically introducing and the particular code is termed as and the particular code is termed as an error control code. Okay, so the particular code, this is termed as an error control code. Okay, so this process is known as channel coding, that is introducing this, systematically introducing the redundancy. The code that is employed is termed as an error control code. Okay, so naturally when you employ encoding at the transmitter, you have to employ decoding at the receiver. All right, so that's what these blocks are. So these blocks constitute basically your channel code. Let's now fill in these blocks. These blocks constitute your channel code, that is your encoder, and this is the corresponding decoder. And out of the decoder you get the, so you have the received message, you decode it, you get the recovered message or the reconstructed message. You can also think of this as the reconstructed. You can also call this as the reconstructed message. Okay. Also observe that each bit, for example 0, is repeated 3 times. In this simple example, each bit is repeated 3 times, implies for every one information bit there are 3 code bits, which is equal to 1 over 3. This is termed as the rate of code. So the rate of the code is basically 1 over 3. What is this? This is basically your number of information bits. You can see what is this. This is the number of information bits divided by the number of output code bits. This is equal to the rate. This is equal to the rate of the code. Number of information bits divided by the number of code bits. This is equal to the rate of the code. Also observe that this is an important aspect, code bits, that shows that at what rate are we introducing the redundancy. Remember, we have to introduce a redundancy. So for each information bit there is a certain larger number of code bits that is generated. That is the meaning of redundancy, right? So this rate is basically shows us what is the number of code bits, number of redundancy, what is the number of redundant bits that are introduced for each information bit. Alright. So if you simply transmit the information bit, there is a maximum possible rate is 1. As the redundancy increases, the code rate decreases. Obviously the number of code bits keeps increasing, redundancy keeps increasing, therefore rate of the code keeps decreasing. Okay, so rate characterizes the redundancy. Okay, so as redundancy as the redundancy increases, right, the rate decreases. Okay, so this is something that you have to keep in mind. So obviously the best code would give the maximum possible error recovery or the best possible error protection for the minimum redundancy, that is lowest possible redundancy, best possible error protection. That would be an efficient code. Okay. Now obviously if you keep increasing the redundancy without bounds, so naturally the error protection, right, for instance if you keep repeating it 5 times, 10 times and so on, as the rate decreases the error protection increases. But we don't want that. We want to have reliable degree of error protection. At the same time limit the redundancy, because the redundancy decreases the bandwidth efficiency of the system. Observe, when you are repeating a bit 3 times or 5 times, let's say, the same bit, right, the same bandwidth which could have been used for transmission of other information bits is now used for transmission of the redundant bits. Okay, so increased redundancy reduces the bandwidth efficiency of the system. That is an important point. Increased redundancy implies a lower bandwidth efficiency. That is something that one has to keep in. Now also observe also that, for instance, you have this 1 which you are repeating 3 times, okay, or let me write it this way, this 1 which has been repeated 3 times. Now if there is a single bit in error, for instance you have 0, 1, 1, this single bit in error you can detect it, because the moment you see 0, 1, 1, it can be the transmitted sequence, 3-bit sequence can either be 1, 1, 1 corresponding to repetition of 1 or 0, 0, 0. Moment you see 0, 1, 1, you can detect an error. So you can detect, and not only that, using the majority rule you can correct it, because 0, 1, 1 using the majority logic this will be bit 1, because the majority is 1, 2 1s and 1 0. So you can also correct it using the majority logic rule. You can also correct this using the majority resistance. However, let's say if you receive 2-bit flips 0, 1, 0. There are 2 bits in error. You can only detect this. You know that something is wrong because the moment you see 0 0 0 1 0, you know that there has an error has occurred. But if you try to correct it using the majority logic decision rule, you will end up with 0 because there are 2 zeros 1 1. So correction not possible, or rather correction will be erroneous. This will be corrected to bit 0, correct, which is basically wrong. Okay, using correction will be erroneous, that is the whole point, because it will be bit 0 which is correct. So 2-bit error, so the point is that I want to drive is 1-bit error can be detected and corrected. So single bit error, so if you look at this repetition code, the larger point that I want to have is, larger point I want to make is that 1-bit error this is both detected plus corrected. However, if you have a 2-bit error, this is only detected but not corrected. So this is only detected not detected but not corrected. So every code has an error correction capability, has an error detection capability, and if you look at here, the number of bit errors you can detect is larger than the number of bit errors that can correct. Obviously, if a bit error can be corrected, then it's necessary to be detected. You can correct it only if you detect it, correct? But if you detect it, it might not be necessary that you will be able to correct it. Okay, so that's the distinction. We'll talk more about these things later, correct, as we progress through several other modules in this course. But the important point to keep in mind is that every code has a bit detection capability, has a bit correction capability. Okay, and if you look at the Hamming distance between the code words, and another way to characterize this is by what is known as the Hamming distance. The Hamming distance is simply number of dissimilar bits. For instance, if you look at our 0, our transmitted code bit 111, 1-bit error, received 1 is 0. So there is a 1-bit difference. So these are same, 1 is same, this is different, implies the Hamming distance dh equals 1. That is basically 1. The Hamming distance between the transmitted and received word is 1. On the other hand, if you look at the second one, that is 111 and 010, 111, and if you look at the second one, that is 010, 10. Now of course these two are identical, these are different. So Hamming distance equals 2. This basically implies 2 different or 2 bits, 2 dissimilar bits, let us put it that way. 2 bits differ basically, okay, 2 dissimilar. This is 2 dissimilar bit. Okay, so the Hamming distance. So the Hamming distance between, so what this says is, in terms of the Hamming distance, if there are 2 bits in error or the Hamming distance is 2, then you can detect it but not correct it. If there is 1 dissimilar bit, then you can both detect it as well as correct it. Okay, so that's a very high level overview of the concept of channel coding and the terminology. What we have looked at is a very simple channel code. There is a repetition code, although it's a code in the strict sense of the word, but it's a very inefficient code. What we will see is there are much better and much more efficient codes, much more efficient in the sense that is have a very low probability of error as well as very low redundancy, that is give the best possible, give the lowest possible probability of error for the least possible redundancy. As we said, this is a metric to characterize the efficiency of the code, and we will see one such code or one such class of codes in the subsequent modules, which are termed as convolutional codes. That is where we are heading towards. Okay, so we will stop here. Thank you very much.